Let's talk about logistic regression. So far, we've been looking at Amy's house prices, and when we predicted those with a linear regression model, house prices could be any real number above maybe $50,000 or whatever the minimum house price was. But there are many cases when we're predicting something and the answer can only be a 0 or a 1. For example, does a patient have a disease or not? Will a share price increase or decrease? Will a customer have an accident or not? I do a great deal of trying to understand that. But if you think about it, even in cases like that, it's not a simple yes or no. Will a customer have an accident or not? Well, a 0 would mean that there's a 0 probability of an accident. A 1 would mean there's a 100% possibility of an accident. And I think typical predictions that I do might be around about 0.2. I think there's a 20% probability that a particular customer will have an accident. So it's a mistake to think that just because you've been presented with data, for example, like the Titanic, where it was either survived equals 0 or survived equals 1, that when you predict, you have to predict a 0 or a 1. Sometimes it can be very useful to predict any real number from 0 all the way up to 1, where the number in between reflects your estimate of the probability. Now, what we're going to discuss in these next two slides, you've actually already seen in practice when you were doing the week 2 assignment on the Titanic. And what you've seen in practice is that when you do linear regression, as we've done so far, and you try predicting what is essentially a probability, you can end up with numbers which are greater than 1 that don't make sense from a probabilistic perspective. But let's just go through this example anyway. Probability of disease equals the intercept, beta 0, plus beta 1 times age, plus beta 2 times height weight ratio, and in the real world there is some noise. Here is an example of a fitted model where we've already determined that the coefficients for age are 0.02, for height weight ratio 0.05, and that there is a 0 intercept. In case where we have age 10 and height weight ratio 3, the probability is the coefficient for age times the age, which is going to be 0.2, plus the coefficient for height weight ratio, beta 2 times 3, which is 0.15, which equals 0.35. So that's fine. That could indeed be a probability. But here's another example. Same coefficients with beta 1 equal to 0.02, beta 2 0.05, but now age is 50, height weight ratio is 5, and the contribution from age times the age coefficient is already 1. The contribution from the height weight ratio is 0.25, and so we get an output of 1.25, which is obviously not a probability. Now, does this really matter? Well, I don't know that it does. If you're trying to predict a probability, you have a problem, but if you just want to know that somebody is at high risk, then surely some high number here indicates that they are at high risk of disease. And you can rank every patient according to this particular score over here, and the higher scores are at higher risk. I remember the very first model I did for classification years and years ago was about whether customers would buy a particular insurance product, and I did it using linear regression, and it didn't matter that I didn't come up with probabilities. But I was able to tell the sales department who was more likely to buy and who was less likely to buy just by ordering the customers in order of this particular score over here. If you do want to predict 0-1, you've already seen how to do that in the Titanic competition. You just define a threshold and you say if score greater than threshold, predict 1, else predict 0. So the fact that your predictions don't lie in the 0-1 range, it isn't a problem in terms of ranking your examples. It isn't a problem in terms of how to predict 0 or 1. It isn't even a problem in terms of if you need to predict probabilities, because what you can do then is as follows. You can group the examples in your training data into, for example, deciles of the score. Maybe your lowest score is -5, so you might have -5 to -2, -2 to -1. I don't know what the deciles will be, but you can split them into 10 equal buckets. 1 to 7.5. In each bucket you'll have the same amount of examples. You can figure out what the average score is in each bucket. The average score here might be -2.5, -1.5, and maybe the average score there is 3. And you can also figure out in your final column here, what is the average response. For example, the average survival in this lowest band over here might have just been 0.1. Average survival in the highest band might have been 0.95, and average survival between might have been going up somehow. I'm not sure if this makes a massive amount of sense, and it's not massively important. What I'm trying to demonstrate here is that even though you have predictions that lie outside of the range 0 and 1, based on your training data, you can map those predictions to probabilities. It's just a little bit painful. Now, despite the fact that we can get away using linear regression on problems where the response is 0, 1, or a number between 0 and 1, it would be kind of nice if we had a way not to need to worry about what we do when the probabilities are greater than 1 or less than 0. And we do have a way to do that. And that is as follows. We'll take our prediction. If you remember, we started with prediction equals beta 0 plus beta 1 x1. But what we will actually do, we're going to introduce a new step and a new word. So we're going to cross out prediction there and put the term linear predictor. The letter normally used for linear predictor is eta. So step 1 is to find our linear predictor in exactly the same way that we used to find the prediction. We now simply call it something else. Step 2 is to create our prediction from the linear predictor. And we say our prediction is e to the eta over 1 plus e to the eta. Let's have a look at why this works. Imagine the outcome of our prediction would originally have been something like 10. Well, 10 is too big to be a probability, it's far greater than 1. But if we don't call it our prediction, we call it our linear predictor, and then we do this to our linear predictor, e to the 10 over 1 plus e to the 10. Do that on your calculator if you want. You're going to find it's very close to, but still less than 1. So we've turned 10 into something which says we're pretty sure the outcome is going to be 1. And likewise, if the outcome was minus 10, originally we would have predicted minus 10, which doesn't make any sense for a probability, but we're not going to call minus 10 our prediction. We're going to call minus 10 our linear predictor, and we're going to do this thing to it. We're going to get e to the minus 10 over 1 plus e to the minus 10. Well, the top is exceedingly close to 0, the bottom is exceedingly close to 1, but a little bit greater than it, and you're going to end up with something which is approximately 0. So we've done exactly what we wanted to do. We've squashed our responses, especially the ones which lay outside of the range 0, 1, into the 0, 1 range. Slightly more neatly typed up for you, we're going to keep the linear prediction, but we're not going to call it our prediction, we're going to call it our linear predictor and transform it into the range from 0 to 1 using this particular transform that you see in front of you. We've been through this. I recommend you try this on your calculator, stick something really small in it. If you stick 1,000 into it, it will make your calculator blow up, but stick something big in it and you'll find it squashes anything you stick in there into the range 0, 1. And in fact, if you put 0 into it, you will end up with a prediction of 0.5. This particular function over here, in other words, f of eta equals e to the eta over 1 plus e to the eta, is called the logistic function, or logistic transform. And by the way, as it says on this slide, the inverse of the logistic function is the logit, which is log of p over 1 minus p. This happens to be the odds of success, and the fact that we have a log in front of here, they would end up calling this the log odds. Many years ago, I worked within a group that had a sister company that looked after credit cards and needed to know the probability that people would default on the balances on their credit cards. In all the work they did, they talked about odds and log of odds. So this was certainly used in practice if you go back far enough, and it's probably still used in practice. As it says on the slide, this function, which is the logit function, which expresses eta in terms of the predicted mean, is known as the link function. So where does this leave us? Well, instead of the good old linear regression, where we just directly predicted what we want to predict, we now have a model which has two stages. Number one, a linear predictor, which is beta 0, beta 1, x1 plus beta 2, x2, and so on and so forth. Number two, we have a function called the link function, which we use to transform our linear predictor into our prediction. And this function, g of eta, is called the link function. I probably should apologize because I promised you a theory-free course, and here was the smallest amount of theory, but it was only, honestly, the smallest amount of theory, and if you don't get quite what we were talking about, it won't stop you using logistic regression in just a minute. But while we're at it, let's think what would happen if, for our link function, g of eta, we used log. So, using the log link, we have log of the prediction equals, we have the log of our final prediction equals the linear predictor. This means that the final prediction is given by e to the beta 0 times e to the beta 1 x1 times e to the beta 2 x2. It means that our final predictions are not really the sum of various effects, they are the product of various effects. Why would we ever want to do that? Why would we ever want to have a model where our final prediction is the product of various things? Well, in car insurance we tend to very much want to do that. You can have a situation where one factor makes a driver 3 times the risk, and another factor makes the driver also 3 times the risk. If a driver has both of these features, they might actually be 9 times the risk, not 6 times the risk, which is what you would get if you had an additive model. So using the log link gives us something called a multiplicative model. Now I'm going to ask you a trick question. If you're doing some analysis and you're not sure whether to use an additive model or a multiplicative model, which one should you use? Hopefully you've guessed what I wanted you to say, which is, I don't know. And therefore, whether the model is multiplicative, i.e. it has a log link, or whether it's additive, i.e. it has an identity link, will be treated as a hyperparameter, and we will set it using the standard train validation approach.